Hi everyone, I'm Taku Noda from Central Research Institute of Electric Power Industry. In this video, I would like to show you 10 practical applications of XTAP. XTAP is a simulation program of electromagnetic transients or EMT in power systems. XTAP is available to everyone for free of charge. It can be downloaded from the website at www.xtap.org, shown at the right bottom corner of this slide. XTAP is an industrial-grade EMT or waveform level simulation program. The slide shows its schematic editor. Using this editor with the parts boxes on the left-hand side, you can create your own power system as an electrical circuit embedded with control systems. XTAP is equipped with a waveform plotting tool with useful functions to show simulation results and a line cable constants calculation tool to obtain electrical constants of overhead transmission lines and underground cables. In addition, XTAP has an automated consecutive simulation function, a statistical simulation function, a PV panel modeling tool, and so on. As explained in the former video entitled An Introduction to the Simulation Program XTAP for the Analysis of Electromagnetic Transients in Power Systems, this figure organizes various kinds of power system simulations in terms of the order of the timescales of phenomena occurring in power systems. For a detailed explanation of this slide, watch the video just mentioned. XTAP covers a timescale from sub-microseconds to tens of seconds, shown by the red circle. If you further magnify this timescale, you get the next slide. Top left, the simulation of lightning over voltages, very fast transients or VFTs, and electromagnetic compatibility or EMC range from sub-microseconds to around a millisecond. At the center, switching over voltages, fault over voltages, and transient recovery voltages or TRVs range from some microseconds to around a second. Right top, the simulations of abnormal oscillations, transformer inrush currents, and temporary over voltages or TOVs range a timescale from milliseconds to seconds. If you look at a little below from the center, studies of controller design and protective relay settings involve from sub-milliseconds to tens or hundreds of seconds. At the bottom, studies of system interconnection and power quality range from sub-microseconds to seconds. Note that if a controller is for power electronics converters used for HVDC transmission, FACTS controllers, and renewable energy interconnections, then the controller must be simulated with its power electronics converters. If this is the case, although I said controller design ranged from sub-milliseconds, the studies should range from sub-microseconds since power electronics converters must be modeled in the simulation. Roughly speaking, XTAP can be used not only for traditional EMT simulations, but also for new simulation needs. The simulations of abnormal over voltages, currents, and oscillations are typical traditional EMT simulations. They include lightning, switching, and black start over voltages, transformer and induction motor generator inrush currents, ferroresonance and subsynchronous resonance. One of the new simulation needs is power quality assessments which include harmonics, flicker, and voltage interruptions, drops, swells. Another new simulation needs is performance studies of power electronics converters. They include HVDC systems, FACTS devices, power electronics converters used in renewable energy generation systems, that is PV and wind, and battery storage systems, including EVs. These are very important for developing smarter grids. Okay, from now on, let's look at 10 practical applications of XTAP. This slide shows simulation project number 1. Large power system simulation, including an HVDC transmission. This simulation was carried out by Shikoku Research Institute and Shikoku Electric Power Company. As shown in the figure at the left bottom corner, the power system of Shikoku Island is connected to the main island system using a 250 kV HVDC transmission system. For the analysis of the HVDC transmission system and also for the analysis of the Shikoku AC system, the entire Shikoku system, including the HVDC transmission system, has been modeled in XTAP. The simulation model is used for various simulation purposes, and the result of a case simulating power flow inversion at the HVDC transmission system is shown as an example. This slide shows simulation project number 2, design of a modular multi-level converter or MMC HVDC transmission system. This simulation was carried out by Hokkaido Electric Power Company. A new HVDC interconnection between Hokkaido Island and the main or Honshu Island is now under operation. It uses modular multi-level converter or MMC technology for the first time in Japan. The entire HVDC transmission system has been modeled in XTAP for its design studies. The results of an AC side fault simulation is shown as an example. Kansai Electric Power Company supplies electricity to highly populated areas, and so underground cable transmission lines are used in many places. Simulation project number 3 is the calculation of zero-sequence circulating currents in underground cable transmission lines. This simulation was carried out by Kansai Electric Power Company. Multiple voltage, multiple circuit underground cable transmission systems installed in a duct are often used in highly populated areas. Such cable transmission systems have been modeled in XTAP in detail so as to reproduce electromagnetic couplings in the duct and impedance imbalance. The ultimate goal of the simulation is to calculate circulating zero-sequence currents accurately for improved relay settings related to zero-sequence currents. The study has actually solved a problem of a protective relay malfunction. A similar simulation, simulation project number 4, was carried out by Tohoku Electric Power Company. In this case, a part of the simulation results was presented in a technical paper. 2 underground cable lines. One is 154 kV connecting substation A and generator station B, and the other is 66 kV connecting substation A and substation C, share the same route in a trench. The cable arrangement in the trench is shown here. For relay settings related to zero-sequence currents, circulating zero-sequence currents due to electromagnetic couplings and impedance imbalance must be assessed precisely. For this purpose, XTAP was used, and the simulation results were compared with corresponding field test results, as in the table on the left bottom corner, and a good agreement was found. This slide showed simulation project number 5, Transformer in Rush Currents. This simulation was carried out by Kyushu, Tohoku, and Shikoku electric power companies. The 3 electric power companies and CREAPI developed a magnetizing circuit model embedded in a transformer model for in-rush current simulations in XTAP. This model is able to reproduce not only in-rush current transients but also ring-down ones. An example of ring-down transient simulation is shown at the center. The simulation result is shown by dotted lines, and the corresponding field test result is shown by solid lines. The simulation result accurately reproduces the field test result. At the bottom center, a comparison between calculated and measured results of inrush currents for different energization timings. A good agreement is found. It should be noted that the parameters of the developed magnetizing circuit model can easily be obtained by utility engineers. This slide showed simulation project number 6, multi-phase flashover of transmission lines carried out by Hokuriku, Chugoku, Kyushu, and Okinawa electric power companies. These 4 electric power companies and CREAPI developed a method to predict multiple flashover phases of a transmission line using the statistical simulation function of XTAP. It takes into account the statistical characteristics of flashover. The flashover phenomenon between arc horns involves statistical delay. In the developed method, the statistical delay of flashover is simulated by random number generation with a normal distribution, and a number of simulation cases are performed to take into account the statistical characteristics. The developed method, in a statistical sense, predicts multiple flashover phases which cannot be predicted by the conventional deterministic method. For instance, the right upper table shows real flashover due to lightning on December 13, 2014. Flashover occurred on the middle and lower phases of the first circuit, also on the upper phase of the second circuit, as shown by the right bottom case in the middle 4 figures. If the conventional deterministic method is used for the prediction, however, it gives the result where flashover occurs on the lower phase of the first circuit and also on the upper phase of the second circuit. If the developed statistical method is used for the prediction, all 4 cases shown in the middle 4 figures are given with probabilities, and the flashover actually occurred is predicted with a probability of 18.3%. Simulation project number 7, studies for the high-power testing laboratory, is shown in this slide. Here at Central Research Institute of Electric Power Industry in Yokosuka, we have a high-power testing laboratory where various tests are performed. The photograph and the main circuit of the laboratory are shown on the left-hand side. We use XTAP for various kinds of simulations as preparation of tests if necessary. This slide showed simulation project number 8, protection relay settings at distribution substations. This simulation was carried out by Hokuriku Electric Power Company. Hokuriku Electric Power Company carried out studies of protective relay settings at distribution substations using XTAP and the smart grid simulator of CREAPI, which we have in Yokosuka. As a result, a formula to predict the sensitivity of the line-to-ground fault relay used by Hokuriku Electric Power was derived, and they rationalized the necessary procedures. Simulation project number 9 is related to lightning protection of distribution lines. The simulation was carried out by Chubu Electric Power Company. Traditionally, communication wires installed below phase wires are not considered in lightning protection design of distribution lines. Since the communication wires are equipped with a metallic messenger wire, it also carries part of a lightning current and thus reduces lightning over voltages. This study first made clear the role of communication wires in the lightning protection design. For this project, we carried out an experiment shown on the left-hand side, and the simulation model was also created in XTAP as shown in the next figure. The simulation results agree well with the corresponding experimental results as shown on the right-hand side. With this study, we better understand the role of communication wires in the lightning protection design. This slide shows the final simulation project today. Simulation project number 10, interference of an SVR and a PV system. This simulation was carried out by Tohoku Electric Power Company. SVR stands for step voltage regulator and PV stands for photovoltaic. It was reported that an SVR, which is operable under reverse power flow, interfered with a large PV generation system. The left upper schematic shows a simplified, relatively long distribution line. Since it is long, it has an SVR at the middle for voltage regulation or compensation. At the tail of the distribution line, a large-scale PV power generation system is connected. The SVR should be operable under reverse power flow, but failed to detect the substation direction. If it fails, it continuously raises the voltage when it has to be downed. When the voltage has to be raised, on the other hand, the SVR continuously downs the voltage. It actually occurred, and yes, it is a problem. The SVR detects the substation direction by measuring the voltages at both sides of the SVR before and after a tap changer operation, as shown in the left figure. The side with smaller voltage change is considered as the substation side. When there were no PV generation systems, this algorithm worked fine. But now we have PV generation systems, and the voltage rises and downs in a short period of time due to clouds. In the figure, if there were no rising trend, the algorithm should work fine. But now with a rising trend, it fails. The phenomenon was produced by XTAP as shown in the right-hand side figure. The cause has been identified by the simulation, and an improved control system of the SVR has been validated using XTAP before installation. Now it works fine. Okay, we have looked at 10 practical simulation projects using XTAP. We are able to introduce these simulation projects since technical papers have been published for them. We also have lots of simulation experience which we cannot disclose. Finally, the website of XTAP is at www.xtap.org. Again, XTAP is available to everyone for free of charge and can be downloaded from this site. Other information can also be obtained from this site. Thank you very much for watching this video. Bye now.